Imagine a network of tiny sensors spread across a vast field, silently monitoring the environment. These sensors, forming a wireless sensor network, collect crucial data like temperature, humidity, and even seismic activity. This data is then relayed to a central base station for analysis and action. But these sensors are often powered by small batteries, making energy conservation paramount. This is where PEGASIS, or Power-Efficient Gathering in Sensor Information Systems, comes into play. PEGASIS is a clever protocol designed to extend the lifespan of wireless sensor networks. It achieves this by organizing the sensor nodes into a chain, allowing for efficient data transmission and minimizing energy consumption. Think of it like a bucket brigade, where each person passes the bucket to the next, minimizing the individual effort. In PEGASIS, each sensor node takes turns transmitting the aggregated data, ensuring a balanced distribution of energy usage. The development of PEGASIS was a significant step forward in the field of wireless sensor networks. It addressed a critical challenge: how to maximize the operational lifetime of these networks given the limited power supply. Prior protocols often involved excessive communication, leading to rapid battery drain. PEGASIS, with its streamlined approach, offered a more sustainable solution. This image helps visualize the chain formation in PEGASIS. Each node is connected to its nearest neighbor, forming a linear structure. This chain-like organization is key to PEGASIS's efficiency. Wireless sensor networks are deployed in a wide range of environments, from remote agricultural fields to bustling urban centers. Often these sensors are placed in inaccessible or hazardous locations, making battery replacement difficult or even impossible. Therefore, maximizing the operational lifetime of these networks is crucial. Energy efficiency is the lifeblood of wireless sensor networks. Without it, these networks become impractical and unsustainable. Imagine deploying sensors in a remote forest to monitor wildlife. Frequent battery replacements would be logistically challenging and potentially disruptive to the ecosystem. The limited power supply of sensor nodes poses a significant constraint on their operational lifespan. Every transmission and reception of data consumes energy. Traditional routing protocols, which often involve multiple hops and redundant transmissions, can quickly deplete the batteries of these tiny devices. PEGASIS, by minimizing the number of transmissions and distributing the energy load among the nodes, offers a solution to this critical challenge. It allows wireless sensor networks to operate for extended periods without requiring frequent battery replacements, making them more practical and cost-effective. PEGASIS stands for Power-Efficient Gathering in Sensor Information Systems. It's a networking protocol specifically designed for wireless sensor networks. Its primary goal is to prolong the network's lifespan by minimizing energy consumption during data transmission. Unlike traditional routing protocols where data might travel through multiple nodes before reaching the base station, PEGASIS employs a chain-based approach. This means the sensor nodes are organized into a linear sequence like links in a chain. Data is passed along this chain from one node to the next until it reaches the designated leader node, which then transmits it to the base station. This chain formation significantly reduces the overall energy expenditure of the network. Each node only communicates with its immediate neighbors in the chain, minimizing the number of transmissions. Furthermore, the role of the leader node rotates among the sensors, ensuring a balanced distribution of energy consumption. This animation visualizes the dynamic nature of the chain formation. The chain isn't fixed. It can adapt to changes in the network, such as node failures or the addition of new nodes. The formation of the PEGASIS chain is a dynamic process. It typically involves a distributed algorithm where nodes communicate with their neighbors to determine the optimal chain structure. This structure might change over time based on factors like node proximity and remaining energy levels. Once the chain is established, data transmission proceeds in a structured manner. Each node collects data from its surroundings and passes it along the chain. As the data travels along the chain, it is aggregated, reducing the overall data volume and further conserving energy. The leader node, responsible for transmitting the aggregated data to the base station, is selected in a rotating fashion. This ensures that no single node is burdened with the energy-intensive task of long-range transmission, promoting balanced energy consumption across the network. The chain formation and operation are designed to be robust and adaptable. If a node fails, the chain can reconfigure itself to maintain connectivity and continue data transmission. This self-healing capability is crucial for the reliability of wireless sensor networks deployed in challenging environments. Section 5. Data aggregation and transmission in PEGASIS. Data aggregation is a key feature of PEGASIS. As data travels along the chain, each node combines the data received from its predecessor with its own sensed data. This process reduces redundancy and minimizes the amount of data that needs to be transmitted, conserving energy. Imagine a chain of sensors monitoring temperature. Instead of each sensor sending its individual temperature reading, they can combine their readings into a single average temperature for a given area. This aggregated data is then transmitted, reducing the number of transmissions and saving energy. The leader node, having received the aggregated data from its predecessor, transmits this consolidated information to the base station. This long-range transmission is the most energy-consuming part of the process, hence the importance of rotating the leader role among the nodes. The aggregation process isn't limited to simple averaging. More complex aggregation functions can be implemented depending on the specific application. For instance, nodes could calculate the maximum, minimum, or standard deviation of the sensed data within their local area before passing it along the chain. Section 6. Advantages of PEGASIS. PEGASIS offers several advantages over traditional routing protocols for WSNs. Its primary benefit is increased network lifetime due to its energy-efficient data gathering and transmission mechanism. By minimizing the number of transmissions and distributing the energy load, PEGASIS helps conserve the limited power resources of sensor nodes. The chain-based structure of PEGASIS simplifies the routing process. Each node only needs to communicate with its immediate neighbors in the chain, reducing the complexity of routing decisions and minimizing overhead. This simplicity contributes to the overall efficiency of the protocol. PEGASIS is also inherently scalable. The chain can easily accommodate new nodes or adapt to node failures. This flexibility makes it suitable for a wide range of WSN deployments, from small-scale monitoring applications to large distributed sensor networks. Finally, the distributed nature of PEGASIS enhances the robustness of the network. There is no single point of failure. If one node fails, the chain can reconfigure itself, ensuring continued operation and data transmission. Section 7. Drawbacks and challenges of PEGASIS. While PEGASIS offers significant advantages, it also faces certain drawbacks and challenges. One potential issue is the latency introduced by the chain-based communication. Data must traverse the entire chain before reaching the base station, which can lead to delays, especially in long chains. Another challenge is the vulnerability of the chain to node failures. While the chain can reconfigure itself, the failure of a critical node, particularly the leader node, can disrupt data transmission and require a reorganization of the entire chain. The optimal chain formation can also be computationally complex, especially in dynamic environments where nodes might move or their energy levels fluctuate. Finding the most energy-efficient chain structure requires sophisticated algorithms and can consume significant processing power. Furthermore, PEGASIS might not be suitable for all types of WSN applications. For applications requiring real-time data delivery, the latency introduced by the chain-based communication might be unacceptable. In such cases, alternative routing protocols might be more appropriate. Section 8. Real-world applications of PEGASIS. PEGASIS finds applications in various real-world scenarios where energy efficiency and long network lifetime are critical. Environmental monitoring is a prime example. Sensors deployed in remote areas to monitor weather patterns, pollution levels, or wildlife activity can benefit from PEGASIS's energy-saving capabilities. Agricultural monitoring is another area where PEGASIS can be deployed. Sensors can be used to monitor soil moisture, temperature, and other environmental factors, enabling precision agriculture and optimizing resource utilization. The long battery life offered by PEGASIS makes it ideal for such applications. In industrial settings, PEGASIS can be used for structural health monitoring. Sensors placed on bridges, buildings, or pipelines can collect data on stress, strain, and other parameters, enabling early detection of potential problems. The robustness and reliability of PEGASIS make it suitable for such critical applications. Even in urban environments, PEGASIS can play a role. Sensors deployed to monitor traffic flow, air quality or noise levels can benefit from its energy efficiency. The scalability of PEGASIS allows it to adapt to the dense and dynamic nature of urban sensor networks. Section 9. Comparing PEGASIS with other routing protocols. PEGASIS, while innovative, isn't the only routing protocol designed for WSNs. LEACH, or Low Energy Adaptive Clustering Hierarchy, is another popular protocol that organizes nodes into clusters, with a cluster head responsible for communication with the base station. While LEACH can be efficient, it can suffer from uneven energy consumption if cluster heads are not chosen carefully. Another protocol, SPIN, which stands for Sensor Protocol for Information via Negotiation, focuses on data dissemination within the network. SPIN is particularly useful for event detection applications, where information about a specific event needs to be spread quickly throughout the network. However, SPIN can be less energy efficient than PEGASIS for general data gathering applications. Direct transmission, where each sensor communicates directly with the base station, is the simplest approach. However, it's highly energy inefficient, especially for nodes far from the base station. PEGASIS, with its chain-based approach, offers a much more energy-efficient alternative. Choosing the right routing protocol depends on the specific application and the characteristics of the WSN. For applications where energy efficiency is paramount, PEGASIS often emerges as a strong contender. Section 10. Future implications and conclusion. PEGASIS has significantly impacted the field of WSNs, paving the way for more energy-efficient and sustainable sensor networks. Ongoing research continues to refine and improve upon its core concepts, exploring new techniques for chain formation, data aggregation, and leader selection. The future of PEGASIS lies in its adaptability and integration with other emerging technologies. Integrating PEGASIS with energy harvesting techniques, where sensors can replenish their energy from environmental sources, could lead to truly self-sustaining WSNs. The development of more sophisticated algorithms for chain formation and data aggregation could further enhance the performance and efficiency of PEGASIS. These advancements could enable even longer network lifetimes and support more complex sensing applications. In conclusion, PEGASIS represents a significant step forward in the quest for energy-efficient WSNs. Its chain-based approach, coupled with data aggregation and distributed leader selection, offers a robust and scalable solution for a wide range of applications. As technology continues to evolve, PEGASIS and its underlying principles will undoubtedly play a crucial role in shaping the future of wireless sensor networks.